Yeah, that's good. Looks good. Okay, so first of all, I'd like to thank the organizers for inviting me to give some lectures here. And this is my favorite kind of setup to talk about physics, namely to students who actually lead the field in very near future, if not already. So I think this is probably what we're talking about is the future of our field. So I'm really excited to talk with you guys. And also, I like it for another reason. It's an informal setup. So please ask questions. And I mean, that's part of the reason I'm giving Blackboard talk and not a formal PowerPoint, is to emphasize the fact that I love interaction. So you feel as unpolished as my writing on the board is, might encourage you to also ask questions if you're shy. So please do ask questions. So it's very informal. So I decided. So part of, I mean, when they asked me to give some talks on TASI, I thought about what are the topics that I feel are important that you may not hear otherwise. I'm sure there are fantastic lectures here, and there are many topics that are being discussed. So I thought, okay, I think that let me try to focus on things that may not be covered by others, and that's the reason I chose this topic, the string landscape and the swampland, for my first two lectures. And this basically is to reconnect or to reemphasize the fact that string theory is ultimately about our universe. That point is sometimes getting missed in recent developments in string theory. It's an amazing tool. It's a very powerful tool. You can do many things with it. You can do condensed matter. You can do, I don't know, plasma gluon and so on, this and that. Lots of different things you can do with it. But actually, the original aim of string theory is getting a little lost. Namely, our aim is actually to understand our universe as is, and not just necessarily view string theory as a tool. Of course, we love to have string theory application in many different areas, so I don't want to undermine that either. That's amazing also. But I think that many of the recent efforts have, in some sense, made it a little bit weaker to the original question. We want to connect string theory to our universe, and we have not made much progress in that area for many, many years. And that's unfortunate, and that's why I think the young crowd should be in that direction, should push that direction as well. Okay, so that's a few words for that direction. And so I would like to mention what we did accomplish, at least. So to bring you up to date, it's a summary report, so to speak, about the status of what has been done, so you would know what needs to be done. And I mean, I'm going to touch on some aspects, so you can view this as a bird's eye view of what has been done. I'm not going to go to too much detail on any one of them. There are references that I put on the website. You can look at those and the references within those and so forth. So you can actually follow if any of these you want in much more detail. So I don't want to give the impression that things don't have a much more detailed structure than the one I'm presenting, but I thought that for my talk, I would just focus on the general aspects of it. So I will start from square one, namely what is the string landscape from the very beginnings, and I will just start even pre-duality era. So start with the basic setup of string theory involving type 2A and type 2B strings, and then type 1 strings, type 1 string, and then heterotic strings. So this is where we started. This is where I started working on string theory. At the time, the emphasis was mostly on heterotic string because it has gauge groups in it, which sounded promising. And type 1 also had gauge group, but sounded somehow not the exceptional gauge group in it, so it sounded less interesting for some reason. I don't know. In retrospect, I don't know why, but anyhow. Heterotic strings sounded much more promising, and people were studying it. And this was a pre-duality, and people constructed, using these starting points, compactifications to 4 dimensions to try to get realistic physics, specifically for heterotic strings. And later, in the duality era, we found that they are all connected into one subject, one object, and moreover, they admitted non-perturbative completions. So the non-perturbative completions connected type 1 and heterotic strings as to one object. More specifically, it connected the type 1 with the SO32 heterotic string as weak, strong, weak dual pairs in 10 dimensions. This is all theories in 10 dimensions. And also, if you went down from 10 to 9 dimensions, the E8 cross E8 theory, heterotic string, and SO32 became the same theory if you turned on suitable Wilson lines on a circle. So heterotic string was unified, type 1 was unified with heterotic, And then type 2A was embedded in the 11-dimensional theory, so perhaps I should go upstairs into a theory which is now called M theory, whose low energy degrees of freedom involves n equals to 1 supergravity in 11 dimensions. And type 2A and type 2B were already known to be connected by going down in a circle by T-duality. This R goes to 1 over R symmetry related these two to one objects once you go to 9 dimensions. And then the M theory was related to E8 cross E8 heterotic string by compactifying. So this was only a circle which was connecting M theory to a type 2A. But if you went down on a circle mod the reflection, it connected to heterotic strings where heterotic E8 comes along, where the two boundaries of the intervals where you get on a small mod Z2 gets identified with 9-dimensional word volumes of an E8 gauge symmetry on each side. This is the Hojawa within construction, and then we have these kind of pictures. So then later there was a slight extension here, namely, if you want to go from M theory to type 2B, you might think, well, you have to do two-circle compactification. So in this case, it seems like almost M theory has everything, except that to try to get to type 1, you have to go a roundabout way and back up here. And from M theory, if you want to go to type 2, you have to go down here to two circles and then back up here. Now, that was not satisfactory. The reason being is that if you take M theory on a 2 torus, S1 times S1, and you squeeze it, you would think that you find a 9-dimensional theory. So if you take T2 and you squeeze the size to 0 size, you think you have 9-dimensional Lorentz invariance, but it turns out you get 10-dimensional Lorentz invariance. So M theory misses type 2B. It doesn't mean it's not connected to it. It's connected, but it does not give you the symmetries of type 2B in any manifest way. So type 2B is a 10-dimensional Lorentz invariance, and it has a coupling complex which can be thought about as a complex structure of a torus because it admits by the strong weak duality more generally have an SL2Z symmetry. So it can be identified as a complex structure of a torus. So then we think about type 2B as if there is a torus, which is you can think about it as a leftover part of this torus whose size has gone away. You just took the life out of it by shrinking it to nothing, but the ratio of the sides is still there. So you think about there's a remnant of that, which is a complex structure of a torus, brings you down to 10 dimensions. So this looks like a 12-dimensional setup formally, and this is what was called F theory. So these, in this way, we get all these things connected into one basic group of objects. Any questions so far? Now, as I said, they're all connected to each other and they're all related. They're all one. There's really one thing. As you can see, you can go from one to the other. I mean, these are the most obvious ones upstairs in 10 dimensions, but you can then start compactifying these theories to lower dimensions and getting other theories. And so it gets very messy because you can have all these different paths of going from one theory up there to the downstairs theory by choosing the intermediate space that you compactify on. So there's a huge number of choices. And so what do we do with these choices? We have to have some organizing principle. And so I would start with some organizing principle. What is the organizing principle? Symmetries that you're left with. For example, if you're left with a d-dimensional Lorentz group, you want to talk about RD on compactified space d dimensions. So that's one way you can distinguish it. So I have a 10-dimensional Lorentz invariance. D-dimension instead of 10 or 11, you get d-dimensional Lorentz invariant theory. So you can say the number of uncompactified, so D is the number of uncompactified dimensions. Uncompactified dimensions. And then another thing you can distinguish is the nature of supersymmetry. So since we know that the theories upstairs in 10 and 11 dimensions supersymmetry played a crucial role in identifying these string theories, it is natural to preserve supersymmetry when we go down in lower dimensions. Of course, that's not our universe. Our universe seems to have broken that supersymmetry, so somehow we have to get rid of it ultimately. And I'm going to say a few things about what we know about that when we try to do that. But we want to count basically how much supersymmetry we are left with in lower dimensions. So the number of supercharges that you're left with is another organizing principle. Sometimes the theory will end up depending on which dimension we are. For example, in even dimensions, occasionally we get some chirality. So supersymmetry might have different chiral versions, in which case we have to distinguish how many supersymmetries of each chirality we are ending up with. So sometimes it's easier just to remember the total number of supercharges. For example, in 11 dimensions, even though I said there's n equals to 1 supersymmetry, the spinor is actually 32 component. So I would just say sometimes I have n equals to 1, or I will say I have 32 supercharges. Okay, so the reason saying that is better when you come down in dimension is because if you compactify on circles, the number of supercharges don't change. But the denomination of what is the supersymmetry in lower dimension changes. So that's a bit inconvenient. So sometimes you want to say, okay, how many total supercharges I have? That's easier to remember, and it doesn't change if you just put circles and so on. If you compactify on periodic boundary conditions on circles, it remains the same. So sometimes I would call that the number of supersymmetries. So this n, we can have two different versions, namely adapted to each dimensions or just the total number of supercharges. So for example, in M theory, which I can view M theory as a non-perturbative completion of type 2A, we have 32 supercharges. And similarly, in the F theory context, we have 32 supercharges as well. Now, these have, in the F theory context in 10 dimensions, which you end up with type 2B, it's actually chiral. Because you end up with 2 units of supersymmetry so this gives you 2A. If you go down on a circle, which has 1, 1 supersymmetry, one of each chirality, but F theory corresponds in 10 dimensions to 2B, which has 2, 0 chirality. So the total amount of supersymmetries are the same, but actually one is chiral, one is not. Okay. Now, so trying to characterize the data by the number of uncompactified dimension and number of supersymmetries is one organizing principle. Now, there could be something intermediate, namely, here I assume that whatever you come down with has a compact geometry. But that's not necessarily the case. You may have some intermediate space which is not compact and still interesting. In fact, most of the efforts, I would say, in string theory, especially in the past 20-some years, has been devoted to the case where this, what we call the compactification space, is non-compact. Okay, so the word is a bit funny, but we use the intermediate manifold is non-compact very often. But that's not good for gravity. And the reason for that is that if you're interested in gravity, if you go down to the lower dimension, the volume of the intermediate manifold, so if you have some intermediate space here, M, so if you start with some M, the volume of that manifold gets related to the Planck constant. So it's basically you have this volume gets in front of the action, you get a term of the form volume of M times the Einstein's curvature, Einstein's action. So this behaves like M Planck to D minus 2. So if volume of the intermediate space is infinite, non-compact, then M Planck is infinite, basically means you have turned off gravity. So now the gravity in the lower dimension is turned off. Of course, you have gravity in the bigger space, but it's not localized to lower dimension. So if you want to get localized gravity in D dimension, you better have a compact space. But occasionally, in studying string theory, we are interested in gauge theory questions, which does not involve gravity data. In that case, we don't care, and we let M to be infinite volume, and that would be perfectly fine. Okay, so so this is the case where we try to get back to d-dimensional Minkowski space. Yes?
But we learned by now that actually even when we don't worry so much about gravity, some local issues
Yes. Yeah, so the intermediate space could be compact or non-compact, and both are interesting, and we are going to study both of them. And I'm going to talk about both of them. I just want to distinguish two cases. And the geometry of intermediate space affects, of course, what we see in lower dimension. In the case where it's non-compact, this gives you a way to study gauge theories and classify them, and has been used very effectively for classifying interesting non-trivial quantum systems we get. And in compact cases, also sometimes it's useful to focus into a piece of the manifold. So it's as if it's you you magnify the whole manifold infinitely large except for a little piece, and then it boils down. The compact problem begins to have pieces similar to the features of the local piece. So the two are not unrelated to each other, of course. And so we'll be studying both of them. But ultimately, you have to decide whether you have the compact manifold, the non-compact one, and that's the question of whether you want to study gravity or gauge theory. That's basically the discussion, and it's useful for both of them. And as Miriam said, the geometry of this intermediate manifold is interesting, independently of which of the two questions you're interested in studying. So here I talked about Minkowski space, RD, but yes?
So you said if you have a non-compact space that you're practicing,
Yes?
then in lower dimensions you have
Correct. Absolutely, yes.
Does that not have any effect at all?
So you have to take a decoupling limit, absolutely. So you have to, so that's a very good question. If you just said that, then yes, indeed, there's a gravity problem. So you have to go to low enough energies to be able to get gravity P. So then only the low energy data could be deduced from it. Now, sometimes you cannot decouple it. In other words, sometimes you might try to do that, to try to decouple gravity when it's non-compact, but it just cannot. And that happens when the theory, the field theory we're dealing with is like asymptotically not free theories. So they are not standalone theories. So sometimes the would-be gauge theories are not good enough theories, and they need a completion. And so then there is a problem. You cannot just have a standalone piece, and then you have to view this as part of connected to a bigger dimensional theory. You cannot just have it on its own. But when the theory, and this is a key point when I will mention later, when the theory is asymptotically free or conformal, then there's a way to get rid of gravity. You can zoom in and you can get rid of the degrees of freedom attributed to gravity by going to low enough energy compared to M-Planck. And that's one of the ways to extract physics out of the compact cases, and that's what I will briefly mention later. So here I focused mainly on flat Minkowski space, but of course we know that there are interesting other cases like ADS. So ADS will have negative curvature. And this kind of geometry we usually get when we only get when we have fluxes in the game. So when you have fluxes in the manifold, some kind of flux, you can actually end up getting solutions of the form ADS times something. And typically this something is negative curvature with a positive curvature, like some sphere or something like a sphere with positive curvature. So you have positive curvature stuff with a negative curvature stuff balancing out to give you a solution to Einstein's equation. You could also ask about de Sitter and something else here. And this actually I will mention later as being one of the, of course, very interesting kind of things if you want to connect string theory to our universe. But as it turns out, this turns out to be one of the most problematic things in the context of string theory. And I will mention about some aspects about this. But for now, I'm going to mainly focus. So the ADS aspects is, I'm sure, well covered by some other lectures. So I will not talk about too many of these aspects about holography and ADS CFD. I will just talk about the flat space version, which is you can view it as a particular limit of this, or more precisely the case where I don't turn on fluxes. I will also come back to the connection with ADS when I talk about, well, maybe I should say it even now. So here I talked about non-compact cases. So the non-compact cases can sometimes be related, if you take a particular geometries of non-compact one, to have related by some holographic duality to ADS geometries. So there's a way to connect them, and typically ADS, even though it looks like it's compact, there is compact, you can actually get it from a non-compact setup. And then the basic example of it in the context of type 2B is when you have parallel DT branes in a non-compact space. And so there's nothing, so the gravity is not dynamical from what I told you. And so you would say, well, but then what are we talking about here in the context of the ADS5 which emerges? Well, in that context, when you have large enough D3 branes and zoom into the region near D3 brane, you get effectively a compact geometry of the sphere surrounding it, and the non-compactness is all localized into one direction that you have drawn out of so one radial direction. So you're basically viewing 6-dimension transfers to the space as to the D branes as a radial direction times spherical direction, and the radial direction becomes part of the ADS geometry. And so the non-compactness is kind of absorbed into this part, and the rest is still compact. And the fact that that sphere has a finite size as you approach the horizon of this near horizon geometry of this D brane is a way to make sense out of this context. So in some sense, you can view these as arising from these geometries when you add branes to the picture. Branes being replaced by fluxes is the statement of holography. Okay, so again, the subject is vast, so I cannot do really justice, but let me just give you some basic ways to think about it. So as I said, one key ingredient. So now I'm going to try to first focus on trying to talk about compact case, where we take this M to be compact. So the dimensions left and the number of supersymmetries. But here is a guideline. We start with the easiest compactification, where the manifold involves tori. If tori, then the counting of dimensions is extremely easy. You just subtract from where you start with to get where you end. And the number of supercharges is the same. So Tn is very easy. So the number of supersymmetries, all supersymmetries, is preserved. Now you can take it more complicated. For example, the next case is the case of K3 manifold. So this manifold is 4-dimensional, and it has SU2 holonomy. It solves the Einstein equation. It's hyperkähler. So it's the first non-trivial Ricci flat manifold, which is relevant for the context of preserving supersymmetry. This preserves. So this has an SU2 holonomy instead of SO4. It's a 4 manifold, but naively would have had SO4 holonomy because it's 4 manifold. But SO4, which is SU2 times SU2, one of them is trivial. And that triviality in SU2 allows you to define covariantly constant spinors on it. And this preserves half the supersymmetry. So whatever number you start with, you get half of it. So if you started, for example, in Hydraulic string, so Hydraulic string already has half of the supersymmetries on F theory because you have overfolded it. So you start with, instead of 32, with 16 supercharges. And if you went down on a K3 further, you would get rid of another half. It gives only 8 supercharges. So that's a quick way to count how many supercharges you'd be left with. So just K3 means half of the supersymmetry. Now, then the next category is the Calabi threefold. So these are Ricci flat, again, Kähler manifolds, which have SU3 holonomy. SU3 holonomy. So you can view this as a Calabi twofold, which is SU2 holonomy. So this is SU3 holonomy. And you might not be surprised if I tell you this preserves 1/4 supersymmetry. And then you have Calabi fourfold. And this has SU4 holonomy, in other words. Kähler manifold, which has SU4 holonomy. The Ricci flat metric, it admits it preserves 1/8 supersymmetry. Another manifold we sometimes use is a 7-dimensional manifold, G2 holonomy manifold. It's a 7-dimensional manifold with G2 holonomy. So let me call it M7 with G2 holonomy. So 7 manifolds typically have SO7 or spin 7 holonomy, but sometimes the holonomy sits inside the G2 subgroup of SO7. In this case, you preserve 1/8 of the supersymmetry. And another case is an 8-dimensional manifold, which has spin 7 holonomy instead of spin 8. And this preserves 1/16. Okay, so this table just gives you, if you choose one of these guys, you will preserve this much supersymmetry. That's the typical. So it's a simple analysis, basically starting with how much supersymmetry you have upstairs, and just counting how many covariantly constant spinors you have on each one allows you to deduce these facts, basically. Yes? They could be compact. Yes. So there are compact examples of these as well. I should emphasize that all of these also have non-compact versions. So the statement applies also to so the counting of supersymmetry applies to whether you're compact or non-compact. That doesn't matter. Okay, good. So at least we can give a quick data from where we start with, namely knowing that type 1 and heterotic have how much supersymmetry, type 2A and type B or M theory and F theory have how much supersymmetry. Given this data, you can create your own table about how much supersymmetry you get in each dimension. And you'll be fine, except sometimes there's a chirality involved. So you get the total number of supercharges, and you have to show whether it's of the same chirality or different chiralities. But apart from that, this gives you a quick way of getting the general structure of it. Yes?
So Yao's theorem rather non-trivially asserts the existence of compact Calabi-Yaos. Do we know about the existence of compact?
Yes, Joyce did that basically. Joyce, it was a non-trivial task, but it has been proven, and there are lots of recent progress in constructing them. But again, these are all existence proofs. Explicitly, it's very difficult. Even for Calabi-Yau, we don't have explicit metrics, except for non-compact. So for non-compact Calabi-Yaus, we do have explicit metrics sometimes. But for compact one, there's not a single case where we know the exact metric. Right. For the smooth version of them, we have no examples for explicit metric. There are singular limits of them, like orbifolds, for which we can write metrics, but that's only singular. It's not satisfactory for mathematicians because it's singular. Okay, good. Okay, so now what do we know? Well, we have a huge amount of choices upstairs and a huge amount of ways to get downstairs. But there is one amazing thing that actually turns you to professional duality builders, namely, anytime the dimension and the number of supersymmetries match, you can conjecture a duality, and you're most often right. Almost always right. That is, if the dimensions and the number of supercharges match, there is one choice of M of one case with another choice of M prime for the other one where they're identical theories. We don't have any counterexample to that statement. Okay? So if you wanted just to predict dualities, just say, oh, it's easy. You just choose a manifold with duality, this much supersymmetry. There must be some M, some other way. They're dual. Why is it the case? We don't know. It's true. Okay, we don't have a counterexample to that statement I just made. It's a very general statement. So in other words, dualities happen. There's hard to prevent them. If two things based on symmetries can be the same, then they are the same. You cannot prevent them. Symmetries are enough to characterize them. It's a very powerful statement. We don't know why it's true. Just by this simple count, you can actually come up with statements. So I'll just give you some examples. So the first example, so in the context of F theory is in 12 dimensions, but there's this funny T2 which is hanging around all the time. So you're allowed to use the same manifolds I told you, except it has to have a torus in the discussion. That is, you have the spaces that basically torus times something. More precisely, it's a torus. There's a fibered space, namely, there's a torus vibration over some base. So that's the context where we talk about in the context of F theory. So for example, K3 has a version which is torus times P1. P1 being a two-sphere and torus is torus. Well, not quite. It's some torus vibration over P1. So there's a description of a K3, which is this one, which can be written actually explicitly, where G and F are some polynomials in Z, and you can think about Z as coordinates on P1, and you can think about Y in terms of X, defining that torus. So this is what we mean by elliptic vibration. There's a torus. Y squared X cubed plus AX plus B is a torus. If you think about the equation satisfying in terms of X and Y, that defines a torus. And it varies as you change Z, and F and G are some polynomials of some fixed degrees. I don't want to discuss what the degrees are right now. It doesn't matter too much. But anyhow, with some specific degrees for F and G, you do get this manifold K3. And that's an example of F theory, compactification. So now what is the dimension? You start with 12 dimension. So now we're going down to 8 dimensions, because K3 is 4-dimensional. But as I just said over there, you preserve half the supersymmetry. So you have 16 supercharges. 16 supercharges is the same supercharge the hydraulic string has in 10 dimension. So you would say, OK, in order to get the same theory, I could do hydraulic on T2. So heterotic in T2 gives you a 16-dimensional theory. Sorry, 8-dimensional theory with 16 supercharges. And it turns out it's dual to this. That's one example. That's the first example. The next example, the same theory. In fact, there is a relation. Now, there's some relations we can use from the upper data. Namely, if you take F theory and compactify it on an extra circle, so you have T2, whatever geometry it has, it gives you M theory based on that same geometry because of this relation going back and forth. So in other words, using this picture, you can deduce that F theory on an elliptic manifold, some elliptic. By elliptic, I mean there's a T2 as part of this, times a circle, is related to M theory on that elliptic manifold. In other words, starting from 12 dimension and using this as a compactification, you'll get the theory which is M theory on just one lower dimensional theory on M elliptic. The same M elliptic. But you don't have that S1 anymore. The relation is that the radius of this circle is related to the area of the torus in this way. So this elliptic manifold has a torus in it, and it has an area. And the area is 1 over r in this relation. So in the limit as r goes to infinity, this radius goes, the area goes to 0. Which means M theory description goes bad, in which case you're back to a higher dimensional theory. So using this, for example, using this link, you can go further down in one more dimension. So another dimension, namely, you can combine the heterotic to be on T3. And then from this direction, you learn M theory on K3 down to the theory in 7 dimensions is dual to heterotic on T3. And that's another truth duality. And there's another chain here. You can go one more step down, which is M theory on a circle. M theory on some manifold times circle is the same as 2A on the same manifold. That follows from the relation upstairs. So then you can do further. You can say type 2A on K3 into a theory in 6 dimensions is equivalent to heterotic. Now you have to go another circle down on T4. So we just got a chain of dualities from upstairs, and using the count of the supersymmetries that they match, you just get some duality statement. Is that clear?
So all of these are kind of gauge groups that are descending?
So there is no gauge group in the original theory, type 2A, type 2. We don't have gauge groups, except on the other side, heterotic does. So the heterotic gauge symmetry is, when you compactify on a circle, it's typically gone. The non-abelian ones are typically gone because of the Wilson lines. You can turn on Wilson lines. So generically, Wilson lines breaks them to the U1s. So at that point, the U1s match the corresponding U1s that you get from supergravity modes and this and that. You can get, they match. The numbers and all that match. Now, if you want to not turn on Wilson lines, you get non-abelian gauge symmetries. And then you can ask where the non-abelian gauge symmetries on this side, and I will come back to it in a second. So there must be a way to get non-abelian symmetries. And as I will mention, this has to do with having these manifolds being singular. So if you're away from singularities, then you don't get any non-abelian stuff. OK, but let's just give more examples. Let's go back to this board. So the next case would be even less supersymmetry. So we have now covered the case where 16 supercharges. The number of supercharges were 16. So now the next case will be 8. So immediately you can think about from the viewpoint of M theory or F theory or type 2 theories. If you want to get 8, you have to get 30 to divide by 4. So you better use Calabi-Yau threefolds. So you immediately go to Calabi-Yau threefold case. So you would think, OK, let's start with Calabi-Yau threefold. So that gives you 8, but heterotic had 16. So in order to get the same 8, you have to divide by 2. So then you use heterotic on K3. So heterotic on K3 should be dual to type 2A, maybe. And you have to also make sure the dimensions match. So heterotic on K3 is 6-dimensional, right? But type 2A on Calabi-Yau is 4-dimensional. That's not good. We want to push it to the same dimension. So what do we do? What do we do? We can compactify on a torus. So you can take K3 times T2. Or if you want to push it up to 6 dimension, what do you do? We want heterotic on K3 to be dual to something in 6 dimensions. What? F theory on what? On what? Calabi-Yau threefolds. Calabi-Yau threefold, which are elliptic. So elliptic threefold, F theory on elliptic threefold should be dual to heterotic on K3. Okay, and that turns out to be true. So I'll give you an example of that. Yes? So it should be true for all C5. I'm saying that, so all CY threefold will give you, elliptic threefold will give you some 60 theory from F theory. Not every one of them is dual to every third, right? There's a dictionary. So each heterotic one will be dual to each elliptic one. Now, there could be finding some exotic one which is not dual to something exotic one. But the general classes, for each one, there's one typically. But there could be exceptions like this one, there's not dual one. That one, there's no dual, and so forth. And this happens. So what I'm saying is at the level of genericity that there will be maps. Yes?
That's just a sort of ADE classification of Calabi-Yau threefold.
So people have tried to give an AD classification, but you mean from the heterotic side? Yes, but it turns out that not all the elliptic threefolds that you get are dual to heterotic ones. There's some subclass of them are. So that was related to the comment I made. So indeed, it suggests that there's some subclass could be related to gauge theory and heterotic strings and K3 and so forth, but not all of them. So how do we describe those? Well, let me just give you some example of how do we think about that. So if you want to compute heterotic, if you want to compactify heterotic strings, it turns out that you have to tell us what happens to the gauge theory. Heterotic string in 10 dimensions has gauge theory. So what do you do with those gauge fields? So you have to choose it. I believe probably Laura I don't know if you have talked already or you're going to give it talks. Okay, so Laura will probably talk about some aspects of these things, so I will not go into too much detail. But when you study heterotic strings in particular, there's an equation that is very crucial to solve. It goes roughly like this. It's dH. So H is the field strength. So as you know, heterotic string is a string. So it couples to a 2-form B field. And there's an H associated with flux. So there's an equation of the form dH is trace of R, wedge R, or R squared, minus trace of F squared. There's an equation like this in heterotic string. So if you don't want to have any source for H, which means that if you don't want to have any 5 branes, so the H is sourced by 5 brane. If you don't want to have a 5 brane, then if you want this class to be 0, then it better be that the Chern classes should match. So the second Chern class of the R, which corresponds to the manifold, tangent bundle of the manifold, should be the same as the second Chern class for the gauge field. So the instant numbers should match to the corresponding that of the tangent bundle. There's a restriction like this. Yes?
Shouldn't you have the Chern-Simons form for the curvature gauge definition?
You're right. I'm being a little bit imprecise. Yes. So with some minor additions here, with omegas and so forth. Yes. Thank you. So, but basically, the main thing I want to emphasize is the fact that the 5 brane is being sourced by it. So this gives you a relation between you cannot do. In other words, you cannot turn it off. You cannot say F is just 0. I don't turn it on. If you have a manifold like K3, if you replace this M by K3, this is 24. So therefore, you have to do something. You have to turn on instanton numbers. So second Chern class of the bundle is nothing but the instant number. So you need to have instantons turned on if you want to have no source for this, if you want to have no 5 branes. And therefore, you have to have 24 of these guys. Instant number should be 24 for heterotic strings. So if you are doing E8 cross E8 heterotic strings, you have to have total number of 24 instanton numbers for E8 or E8 times E8. So you can distribute them. You can say I have K of the instantons here and 24 minus K instantons on this guy, and that would be a consistent choice. It turns out that each choice of K, when you do it, will give you a different dual elliptic threefold. So it depends on which choice you make on the heterotic side. So for example, if you choose K equals to 12, the most democratic distribution, 12 on each. Turns out to be a very simple example. It corresponds to the Calabi-Yau threefold, which is basically P1 times P1 to 2 spheres times a T2. Where by T2, again, I mean the product. Namely, there's elliptic vibration over P1 times P1. So that's a simple example of this duality. So you can see that this kind of can be viewed as coming from the original duality that I told you about, namely F theory on K3, which is this, was dual to hydraulic on T2. Then you can multiply this, fiber this over a P1, and so this was T2 on the hydraulic side. You fiber this over P1, now you multiply it by an extra P1. Then this becomes K3, and this becomes the Calabi-Yau we talked about. So in other words, once you start with the duality upstairs, you can fiber it, that theory in 8 dimensions, over a P1 and get the duality in 6 dimensions. And that's another way of getting new dualities. Basically by what's called adiabatic procedure, namely you start with the duality upstairs and vary the data gradually and get the duality in lower dimensions. It turns out this adiabatic argument is very powerful and gives you a way to get new dualities from higher dimensional dualities by varying the data over some manifold. It's hard to argue why it works, why even that works, because, well, you might say adiabatic argument, that sounds reasonable. You go slowly, you change something on both sides, so it should work. Except that always, when you do interesting stuff, there are some points where it has to rapidly change. So it's never adiabatic. So it sounds good in words, but actually in reality it's not adiabatic, but still works. So adiabatic is violated, but for some reason it still works. Why? We don't have a deep understanding. Again, based on number of supersymmetries and supercharges, dimensions and so on, as soon as that matches, everything works. Good. So this lands us on theories with 8 supercharges, and then you can do the same thing I talked about, namely going to M theory by adding an extra circle, or going to type 2A by adding an extra circle, so you can go from 6 to 5 to 4 and so forth. So then this gives you theories with 8 supercharges. Now you can say I want less supercharges, and we can do that too. Yes. What is what? Okay, thank you. Thanks for the question. I actually meant to say something about it, I forgot. So suppose DH is not 0. So what happens? Well, so H is not equal to 0. It has the following feature. So let's start with hydraulic M theory description hydraulic string. So in 10 dimensions, if you want to get E8 cross E8 hydraulic string from M theory, you put it on an interval. This is the Hojawa-Witten construction, where you get E8 on both sides. So that's the E8 times E8 from the M theory. It gives you the 10-dimensional description of hydraulic string, right? You put all of this on K3. So you go from 10 dimensions down to 6 dimensions by doing that. You come down the same thing. So the space is basically interval times K3. That's your M theory perspective. So from M theory perspective, you put it on interval times K3. Except you have to give a bundle data. What do you do with this bundle? Well, the bundle is turning on instant-time numbers on E8. So turning on instant numbers on E8, you're doing something on the edges, on the 2 edges. So it's very hard to describe it using M theory, because you don't see the E8 degrees of freedom so easily in M theory. But in principle, there's a way to do it. Now, so roughly speaking, there's an instanton number 12 here, and instant number 12 here. But you can actually do something. You can take these instantons, they have sizes inside the K3 and so on, and you can shrink them to 0 size. So once instanton shrinks to 0 size, it is ready to be ejected from the boundary as a 5-brane. So you can take in these instantons one by one. You can decrease this to 11 by taking one instanton which has 0 size and bringing it out on the interval. So now you can create M5 branes, which is what is sources DH in the language of. So the DH that I talked about in the language of type 2A, language of hydraulics is a 5-brane, but it's the same also in the language of the M theory. So that you can eject one Instanton out to the fibrane. Fibrane out on this interval. In fact, you can make it move over to the other side and then grow size. Right? So you can go from 1212 to 1113 and so on by moving this fibrane on the interval to the other side. And then you might say, wait a second, I just violated what I had told you. I told you for each k, I just get the geometry, and I only told you what's the answer for k equals to 12. What about for k equals to 11 and 13? It turns out that this procedure of bringing this out and over there involves Calabi-Yau geometry transitions. You take P1 times P1, you blow up and blow down a point geometrically, and you change the topology of the Calabi-Yau threefold, and that blow up and the blow down corresponds to moving this from one side to the other. So ejecting corresponds to blow up, and absorbing corresponds to blow down in geometry. So beautiful match between the data, geometry data, and what you would think in terms of brain data. Of course, these are hallmarks of duality. The language looks very different, but they all match. Sorry? Sum is still 24. So you can do that too. Yes. Yes, there's a Calabi-Yau geometry. So the geometry here is P1 times P1, I told you about. But it turns out that if you change this to Fn, Fn is the generalization of these Hirzebruch surfaces, which generalizes P1 times P1. I don't want to describe it too much. It's roughly P1 times P1, but the P1 is fibered over P1. So it's roughly P1 fibered over P1. So it's generalization of this one. And these Hirzebruch surfaces are what is needed in trying to describe all the different Ks. So as n goes from 0 to 12, gives you the instanton number, n equal to 0 corresponds to P1 times P1. That's when you have 12. But when you go all the way up to 0 and 24, then you're talking about F12. So they're all described by these geometries. Yes? Well, that would be a totally different, slightly different geometry we are talking about. But so we are talking. So there's a case where DH is replaced by the fibrane. That's what I was talking about. But there's also another set of solutions. I don't know if you're going to talk about those also. So there are cases where you actually have non-trivial extensions of Calabi-Yau, where you turn on H flux, not necessarily brain itself, which takes a deficit of this and turns in terms of some form, and then gives you some slightly different equation that people have studied, and Laura is going to describe it in her talk. So here I was just talking about when they are actually sourced by fibrane itself. Any other questions? Good. Okay, so this gives you, so there's one, before I move on, I have talked about 32 supercharges, 16 supercharges, 8 supercharges. Well, 4 supercharges is interesting. Why is that? Well, that's the case people try to study in the context of phenomenology. Why? Well, in 4 dimensions we live in, n could be 1 or 2 or 3 or whatnot, but n bigger than 1 has a problem. Number of supersymmetries more than 1 makes the theory non-chiral. But we know the phenomenology is chiral, so we want with at most n equals to 1. So we can have n equal to 0 or n equals to 1 at best. So n equals to 1 supersymmetry in 4D is crucial for trying to connect to phenomenology. So n equals to 1 with 4 supercharges has 4 supercharges, as you can count, because you have one supersymmetry, and that's 4 supercharges. So we want to get 4 supercharges. That's useful for phenomenology, and that has been studied the most in the context of string literature in terms of trying to understand it. I'm sure you will hear more about it from Dora. But let's see, how do we get 4? For heterotic strings, you want to start from 16. You want to get down to 4. So you want to have 1/4 supersymmetry. And 1/4 supersymmetry involves using Calabi-Yau threefolds. So that's why originally heterotic strings on Calabi-Yau threefolds were studied quite a bit. That's one example. Now, but of course you can do other things. For example, if you want to start with some other geometry, you can use 1/8. If you go with higher supersymmetry like 32, you can use 1/8. But you need to land in 4 dimensions. So if you use Calabi-Yau fourfolds, that won't do the job. From M theory, if you go from 11 minus 8 dimensions, you end up with 3 dimensions, unfortunately, not 4 dimensions. So that doesn't quite work. So what can you use? You want to end up in 4 dimensions. F theory. So F theory on Calabi-Yau fourfolds, it's my favorite. F theory on Calabi-Yau fourfolds, you will give you four-dimensional theory, and it will match the number of supersymmetries you want, namely 4 supercharges. And that's why one of the main cases for phenomenological application is studying F theory on elliptic fourfolds. But not all is lost. In fact, luckily, G2 steps in, says, wait a second, M theory is not so bad. I can use G2. Why is that? Well, G2 is 7-dimensional, just on the right number. 11 minus 7 is 4-dimensional, and the number of supersymmetries is exactly 1/8. Again, it works. So you can use M theory on G2. Again, there are dualities, as you might expect. Again, I should say not every one of them is dual to some other one, but basically that class has dualities among them. So M theory on G2 on a manifold gives you n equals to 1 in 4 dimension, which is dual, potentially, to elliptic. F theory on elliptic fourfolds, or heterotic on elliptic, or heterotic on Calabi-Yau threefolds. So you have a triality of duality. There are three groups you can dual to each other. Is that clear? So I hope by now I have given you a feeling that's not that bad, okay? It is not that bad. You can actually begin to now go down to 3 dimensions. I will leave those exercises to you. What do you get in 3 dimensions, or maybe in 2 dimensions? Can you come up with dualities? Maybe nobody has studied it enough. Maybe you can study. Yes? People have studied examples of G2. I'm not sure if you're going to talk about any of those or not. No. There are dualities. And basically, you can start with higher ones and just study various versions. So people have studied, conjectured. G2 manifolds are difficult to study. The reason is that they are not complex manifolds, so the real data is hard to deal with. So it's not going to be that simple, but it's nevertheless some people have studied it. Now, so there is a lower dimensional cases that you could study, 3D and 2D and so on. But I will, as I said, I will leave that as exercises to you. And in fact, it's fun exercises. Hopefully, you'll get some fun out of trying to construct some possible dualities. Good. Now, okay, so let's see. Wow, time flies. I'm not even halfway. Okay, so I will have to speed up. Okay, so now let me talk about something else, which is related to what I described, which is the connection with branes. I mean, so far I've emphasized geometry, except for the a brief comment I made about the 5 branes. You might have said this has nothing to do with branes, you're just talking about geometry and so forth. But actually, one of the beautiful things we discovered in the duality era is dualities between branes and singularities of manifolds. So you can replace a singular manifold by branes. In fact, you can define new branes by singularity of manifolds, which we had not known about before. So manifolds and their geometry, when they are singular, even though mathematicians want to avoid at all costs, we welcome them at all costs, because precisely that's where we get new physics. Singular manifolds are where you get new physics. That's why the exciting stuff is for us. So, so let me try to go over here. So this first example is the most basic example is this. Take C2 and divide it by a subgroup, discrete subgroup of SU2. For example, you can take a discrete subgroup of SU2 which acts on the 2 coordinates Z1 and Z2 of C2. So I'm taking the coordinates being Z1 and Z2 by some nth root of unity. So this gives you a singular space, because at the origin, when Z1 and Z2 is 0, you're identifying a space by this action, and the singularity corresponding to the one I just told you about, when gamma is Zn, this is what's called an An-1 singularity. So the singularity of a geometry, and it turns out that this thing is dual. Depending on how we realize it, is dual to, so let me just give you a very concrete one. So take type 2A on C2 time mod gamma of one kind. This will be dual to having type 2B on with ND5 brains. Now, I have to be a bit more precise. You may, to make this duality to be precise, you actually need to have one of the C's having a compact circle in the game. So this is roughly correct what I just said. So basically, it's true. Namely, you might have slightly more elaborate data than C2. You might have to involve something like what's called tab knot space, but morally it's like C2. So there's a duality between them. ND5 brane gives you a gate symmetry. As we know, if you take D branes and put them on top of each other, you get SUN gate symmetry. And this is dual to this data. At the singularity, you have restored the gate symmetry. And how does it work here? Well, it turns out if you want to take this, if you blow up this geometry, so you get a bunch of spheres. You get n-1 spheres out of the blow-up geometry. And you can get D2 branes wrapping around these cycles or glued together, which play the role of the off-diagonal parts of the abelian symmetries to enhance it to an SUN symmetry. So roughly speaking, you can think about these as having the points where the branes are, and these D branes as the string stretched between them. So the geometry becomes beautifully matched with respect to combinations of the branes wrapping around these cycles and the circles, and you can get that by basically shrinking that circle along the line and doing some dualities. You can get literally the map between branes and singularities. Okay? So that's quite remarkable. And you can do similar versions. For example, you can do something involving D singularities, and you get some SO gauge group in this case, and that you could obtain, for example, using orientifolds. But you can also get E gauge group. If you take, instead of the dihedral group, you can take cyclic group here I did, you can take dihedral subgroups of SU2, or the three exceptional subgroups of SU2. On the left side, you get E gauge groups, E6, E7, E8. On the right side, good luck. Well, it's going to be hard to describe them using branes. We don't have easy ways to get gauge groups of E6, E7, E8 using branes. But geometry is in the same footing. So from geometry, you get them the same way. So somehow, the connection between geometry and brane is very useful. It tells you that you can get a perspective about gauge theories and branes in terms of singularities of the manifold. Now, this is actually quite interesting because the F theory data, for example, I told you I have not talked about F theory data about branes when I was talking about F theory and type 2A and M theory and all that, but actually I was. Because it turns out F theory on elliptic manifold is nothing but type 2B with 7 branes in them. So 7 branes were turned on. So you see, that's one of the things about the F theory was actually to have branes in the geometry. You could replace the elliptic fourfolds in terms of geometry, basically using this data. So if you push this data in the elliptic context, you'll actually get the context in which F theory on elliptic manifolds gets related to type 2B with 7 branes. So it turns out in terms of 7 branes, you can have what is called P, Q 7 branes, depending on which kind of 7 branes you use. Putting them together, you can get exceptional gauge symmetries like E8. But that involves using some non-trivial kinds of 7 branes, PQ. So they're not all D branes. But you can combine 7 branes of different types, and you can get E gauge symmetry. But it's not perturbatively accessible. We cannot understand them perturbatively. Now, this is actually one of the original problems we had before. See, so I said type 2B has 7 branes. But 7 branes have charges, and they give you fluxes. But maybe when you studied general relativity, they told you that you cannot have charges in a compact space because the flux has nowhere to go. Have you all studied that fact? Yet I'm telling you that 7 branes in a compact sphere makes sense. For example, in the context of K3, the type 2B perspective is a sphere. And at some 24 points, you have some branes. And I have no problem with the flux. What happened? So that's actually an amazing way. So it turns out these fluxes are non-abelian. And so they cancel each other out as you go around. So you can have non-trivial charges. So that evades that general relativity theorem, because that involves only abelian charges, and these guys involve non-abelian monodromies. So you can actually put them together and get a perfectly well-defined object out. Okay, so very good. Let me go on. So this connection between geometry and brain is very powerful, and you can use this kind of picture and go down to lower dimension and then use brains ending on each other to get some other geometry. So there's a beautiful interplay between geometry and brain. I'll just give you one example, just to give you some class. So here I talked about P1 times P1. So you might take, for example, M theory on a non-compact space which has a P1 times P1 in it. So Calabi-Yau manifold, which is the bundle called O minus 2 bundle over P1 times P1. This is just a piece of a Calabi-Yau threefold. And this turns out to be a theory in, if you go down from M theory in 11 dimension on a 6-dimensional manifold, which this is a piece of a Calabi-Yau threefold, you get a theory in 5 dimension. This is now a non-compact case. And this turns out to be dual to type 2b in 5 dimensions, where you have put brains, and the brains you put are like this. What do I mean by that? Well, you take type 2b, you choose 5 brains. Now, 5 brains of type 2b come in varieties called p comma q. So the 1 comma 0 type, let's say, is d5 brain, and 0 comma 1 is ns5 brain, and then you can bound the d5 brain with ns5 brain, and that's called the p comma q5 brain. So it turns out that if you take a 5 brain is what dimension? What is it dimensional? 6-dimensional. I want to get a 5-dimensional geometry. How do I do? So I have 1 extra dimension left over. So I put that extra dimension as part of 2 of these extra dimensions. So I split type 2b into R5 times R5. So this is the space-time I want to be left with. I choose an R2 inside this R5. And on that 2-dimensional plane, I put 1 dimension of each 5 brains. So I choose 5 brains to wrap the R5 with 1 extra dimension left over as part of R2, which I'm drawing here for you. So these are brains of different type. This type you put 1, 0 brain. This part you put 0, 1 brain. This part you put 1, comma 1 brain, and so forth. So it turns out you can choose the direction of the brains to correlate with the corresponding slope. And you get a geometry which is dual to P1 times P1. So this corresponds to 1 P1, and this corresponds to the other P1. So you get the geometry in this way. So this is called the web construction of PQ5 brains, which is dual to descriptions of M theory and Calabi-Yau threefolds near the singularities. You can study either way. Why is that interesting? It turns out it gives you, when you shrink it down to 0, when you shrink the P1 and P1 to 0 size, this geometry, or equivalently to that brain geometry, gives you conformal theories in 5 dimensions. So you can construct new theories by taking these kind of configurations, go to singular limits of manifolds, get new theories in various dimensions, including 5.
Which new means they don't have Lagrangian.
New means in 5 dimensions we don't have any Lagrangian of any conformal theory. Yes, that's the basic point. Now, it turns out that there's an effective description of them away from the conformal point. So, for example, this turns out to relate to SU2 gauge symmetry in 5 dimensions. And so the way you think about it, if you think about this D5 brains, you can think about this as strings stretched between them. So this looks like SU2 gauge symmetry. It's the usual way 2D brains can give you SU2. So this, in the brain picture, gives you SU2 gauge symmetry, but then you shrink it to nothing. And the coupling constant of gauge theory is 1 over g squared. You're taking, therefore, infinite coupling. Then you shrink the 1 over g squared to 0 size. And therefore, you're talking about infinitely strong coupled SU2 gauge theory in 5 dimensions, which would be the conformal theory. So we don't trust the description in terms of gauge degrees of freedom at that limit, but morally, it flows to it in the infrared limit. Namely, if you let the coupling to be finite and let go to infrared, then you get an effective description a la SU2 gauge theory. Okay, good. I was going to talk about phenomenology and F theory. I guess I'm not going to talk about it because I don't have time. Somebody else will, I'm assuming, right? Sorry? Timo will go. Good, great. So I'll leave the discussion for the phenomenological application to F theory. But one point I would just to make sure I will just mention is that one motivation for the description is, and this connects to the local description versus compact ones. It turns out that the particle physics for the standard model and so forth is asymptotically free. So basically, it means that you don't have too much matter in that gauge group, but you could have had. Typically, when you compactify string theory on manifolds, you get many, many matter for a given gauge group, and therefore it's not asymptotically free. You cannot decouple gravity. But it turns out that, as a given fact, our universe has gauge groups with matter which are asymptotically free. Therefore, it will be of the kind where we can just take a non-compact version. So we can have a non-compact version of the manifold describing our universe, which suggests that our universe, since we have a gravity which must come from a compact geometry, the relevant piece for us comes from a little corner of it. So there's some little geometry inside this compact geometry describes our particle physics. So that if that's the case, it helps us in studying only that little piece if we wanted to talk about our universe. So that gives you a way to think about local ones. But of course, for the full model, you have to talk about the full compact geometry if you want to get some mileage. And it turns out, and this is the topic of the afternoon, not every local thing you write down could potentially come from the compact one. So you will make a mistake if you say, oh, I just construct the compact local one, and there must be something which works. No, that doesn't necessarily work. And I'll give you counterexamples to that statement in the afternoon. Needless to say, some symmetries of particle physics get related to geometry. For example, when the 3x3 mass matrix for the 3 generations of particles have some approximate U1 times U1 symmetries called Frogat-Nielsen symmetries. In the context of these constructions, these U1 symmetries correspond to approximate rotation of internal space. So the internal symmetries of rotations of the Lorentz group of the internal manifold becomes approximate symmetries that we observe in particle phenomenology, and that's very satisfying potential connection between symmetries, because we know there cannot be exact global symmetries in the context of compact manifolds, in the context of string theories. Calabias don't have these compact circle symmetries, but approximately there is. And that's exactly the only kind of symmetries that they do see in particle physics, which is approximate circle symmetries. So in the last 5 minutes, let me talk about what we really want, which is breaking supersymmetry, okay? That's what we want. I mean, this is all nice and beautiful, but actually, it's not still our universe, and this is the one we want to do. We want no supersymmetry. What do? Well, we break it. We break it, and we broke it even before the duality era came in. So from early days, we were trying to construct, in string theory, non-supersymmetric geometries. And it was very easy. What do? For example, you take tori, and you can put non-periodic boundary conditions around the circle instead of periodic for fermions. You take fermions and instead of making them periodic, make it non-periodic. And then in the lower dimensional theory, because of that anti-periodic boundary condition, you got rid of zero modes. You don't have supersymmetry. You kill supersymmetry by hand. It's called the Shirk-Schwartz mechanism. So you break supersymmetry. What's the problem? Well, no problem, except that you can change this radius, and you find that at some critical radius, the theory develops a tachyon. Okay, so you say, well, avoid it. Don't go there. Well, you don't have. You have to study it because it's part of the radius modular. The change of the radius is part of your story. So you end up studying tachyon. You say, okay, maybe you were not clever enough. Don't do the circle. Do something more exotic, like orbifolds, like the one I just told you about. You think C2 mod gamma. So if you choose SU2, you get supersymmetric ones. But don't choose SU2. Just choose U1, something which doesn't sit inside SU2. Then you break supersymmetry. Great. What about that? Well, it turns out each time you did that, you again get tachyons. You get tachyon, which means what? It means your solution is not stable. Okay. Is there a conspiracy? Each time we break supersymmetry, there's no solution. Why? It could have been perfectly non-tachyonic. It's not. Okay. We have perturbative control. We could have gotten it. We didn't get it. Okay. Is string theory giving us a message? I strongly believe so. After spending many years with the getting rid of my hair and all that, pulling it and so on, trying to understand why we cannot seem to get a good non-supersymmetric situation. We seem to always get tachyons or this and that. Okay. So how do we deal with it? So people have tried to do it. So KKLT in particular is a construction where it basically starts with some Calabi-Yau geometries and maybe some fluxes involved. So it's supersymmetric. They start with supersymmetric description. Everything is nice. With n equals to 1 supersymmetry in 4 dimension. Beautiful. We can trust that and so on. And then they introduce element which breaks the supersymmetry by hand. Like they say, oh, what if we add an anti-D brane instead of a D brane? So the wrong sign of D brane breaks the supersymmetry. They put anti-D3 branes in some place in their geometry. They put it there. They break supersymmetry by hand, and they go from a geometry which used to be anti-de Sitter by putting these anti-D branes. They lift the energy up to positive energy, and you can get positive energy, which looks like our universe, de Sitter, with no supersymmetry. So what's the problem? Well, the problem is, you see, you have to know all the moduli to control them. And these theories, unfortunately, the ones that they study, have humongous number of moduli. And putting these things in the game, you lose control over studying it. So in the context like KKLT, unfortunately, we do not have analytic control. And in the cases which we do have analytic control, like the ones in string theory, you get things like tachyons. Okay, so now you can have two perspectives. Well, we're not very smart. KKLT is perfectly fine. We just don't know how to analyze it. Possible. Cannot. I mean, it's hard to prove something you cannot study. It's easier to say maybe it works. If you want to be optimistic, that's the case. But on the other hand, we have run into these problems. So what is the outcome? How do we get our universe? Where do we get our de Sitter space that we want to have with properties that we want to have? This is a big mystery for us. So this is a part that I will actually make some comments about in the afternoon about the connection with Swampland and breaking supersymmetry. How do we get to that stage? But that's probably the most exciting part of the landscape, which we have not studied much in string theory. So after all these years, after, I don't know, more than 30-some years of studying string theory and this landscape, I have to admit I'm frustrated by the fact that we have not been able to get where we want in terms of non-supersymmetric ones. And the constructions in the literature, which suggest that's okay, seems to run into troubles when you really study them in detail. So it seems to me to be a cautionary note that you should not necessarily believe you have understood this non-supersymmetric situation, though there's a noble cause to try to understand it. So I think, given that I have run, the time is up, right? Is that correct? Yes.
What about the large volume scenario?
Large volume scenario is part of what I mentioned in terms of the basic things that one does is studying the local geometry inside the manifold. So more or less the same kind of game. So perfectly fine. But again, the issue of understanding supersymmetry involves understanding all moduli, and that's the problem. You have these modes, like the Scherk-Short mechanism. You have a circle. You cannot just say, I hold a circle by my hands, I don't let it shrink. It might shrink, or it may grow. Okay? You have to stabilize it, and that's hard. We do not have an effective mechanism of stabilizing in a situation where we trust with a non-supersymmetric situation. That's our problem. So I think, given that I'm out of time, I would love to go on more and more, but I'm going to tell you a few things later in the afternoon anyhow, so I will stop for now. Thank you.
We still have time for a few questions.
Yes?
So for the KKLT mechanism, how do they avoid action?
So the story. So let me just explain it first of all this way. So anti-D3 doesn't introduce tachyon by itself, right? So if you take flat space, put an anti-D3, there's no problem. So that's the first answer. So anti-D3 by itself does not cause a problem. The problem arises when you look at the full geometry and whether the moduli of the D3 brane, whether it moves around or not. Is it stabilized or not? If it's stabilized, the position of the D3 brane, have you stabilized the size of the manifold? Could that shrink or not? And so forth. So I'll give you one example of this class, which is actually I have studied. So you take a Calabi-Yau. Calabi-Yau have cycles in it. So sometimes the cycles are in the same class. So first of all, putting a brane or anti-brane is problematic, because if you put anti-brane inside, add one brane in a compact geometry, it creates flux. And then there's a problem that you cannot have a flux in a non-compact space. So if you put extra brane on a Calabi-Yau, you have to put the anti-brane. But you can put an anti-brane not on the same cycle, but in the same class cycle, you put it somewhere else. Okay, so you have brane here and anti-brane here. Great. Now you say, why they don't come to each other and touch and get rid of each other. There's a good reason they can avoid that. Namely, it turns out that some of these spheres where they wrap around, if you want to move around from it, it grows in size. So that means the energy goes up. That means you have to climb a potential barrier. That means the brain and an anti-brain separated is okay. So I was almost so happy. It's great. I've constructed this stabilized, non-supersymmetric one. Problem. How do you know that the moduli of Calabi-Yau doesn't bring them together? So precisely as you put brain and anti-brain, the moduli become dynamical. They're not flat anymore. Then it's a roll again. So as soon as you put brain and anti-brain, you have to understand why and how you're stabilizing at the minimum. And so you kill one problem, you create another problem. It's so frustrating, I tell you.